Hello everybody, my name is Ana Cecilia Valdez and this is my lab number 2, motion of a falling object for Physics 2211. The purpose of this lab is to explore Newton's second law of motion by modeling motion in three different ways. First, we will track observed motion with tracker, and then we will use Google Script to capture predicted motion. One version that considers drag force and one that does not consider drag force. Overall, our results indicated that the model that best represented real motion was the one that considered drag force. This is because in the real force, drag is consistently present as air resistance. The major concepts used for this lab are those that have a direct relationship with force. For example, position, we use the position update formula, which is position final is equal to position initial plus the average velocity times delta t. The velocity update formula, next, is just that the final velocity is equal to the initial velocity plus the net force over mass times delta t. Then the drag force, we have that it equals the negative b, which is our proportionality constant, times the object speed plus v hat, which is just the direction of velocity. And finally, our gravitational force is just Fg is equal to the negative gravitational constant, which we have here 9.8 newtons per kilogram, times mass times j hat. As you can see, this is our experiment. It takes place on our physics classrooms, and we will be describing the system and surroundings in the next slide. Well, in this case, our system is a plastic ping pong ball that has a mass of 2.7 grams and 4 centimeters of diameter, and our surroundings are the physics classroom. Here we have a free body diagram with an indication of the force of gravity and force of drag. The initial conditions for the predicted motion are the following. For mass, we have 2.7 grams, which is 0.0027 kilograms. The velocity and position are at the origin. Then our gravitational constant is of 9.8, and our proportionality constant is equal to 0 because we're not considering drag. This graph shows the observed motion and the predicted motion considering no drag. Both of these are functions of time. It is evident that these functions are not the same. The position in the predicted motion goes farther down the y-axis as it is not considering drag. And well, what this means is that the predicted motion only has gravity, therefore it goes faster, but in the actual experiment, the motion is slower because of drag. For the predicted motion that considered drag, we used the initial variables almost the same as the one that did not consider drag, except we included a proportionality constant that's non-zero, and we added the drag calculation, which is just negative proportionality constant times a magnitude of the velocity squared times negative j hat because we're going on the negative y directions because the object is falling down. In the case of this graph, observed motion and predicted motion considering drag are shown. These curves are very similar, as you can see, because of the predicted motion model considering drag, which drag now we know is present in the real world in the form of air resistance, and while the real world was the scenario where the experiment took place in. Just to conclude, the possible sources of error that could have occurred in this lab were that filming was not entirely still the entire time, which could have moved a little bit our axis, and also the system, the description of our system, the weight and the diameter might not be exactly as it is in reality because we had to research them in internet as we were not able to determine them during the lab practice, and also the drag that we don't know exactly which is a constant as we could not measure it in the real world.